All right, hey guys, I'm sorry to have to do class this way. I was feeling really bad when I woke up this morning, and I'm scheduled to get tested later, so we'll see. Hopefully class will be back to normal next week. All right, so last time we learned Ohm's law, that the current going through a conductor is proportional to the voltage across that conductor. And we saw that the constant of proportionality was 1 over the resistance. So this is the resistance. It's what resists the flow of electricity. So the actual origin of this is that as the electrons try to travel through a conductor, they can bump into each other, they can bump into nuclei, they can bump into random things that slow them down. And so this sort of resists it. And from a microscopic point of view, the resistance is equal to the resistivity times the length of our wire divided by the cross-sectional area. So this rho, our resistivity, is something that's inherent to the substance. So for instance, copper has some value of it, gold has some value, everything has some value, including non-conductors like plastic or rubber. And last time, that's just all it was. This quantity has a different value for different materials, but it turns out in reality, there's some temperature dependence to it. So you can imagine as a conductor gets hotter and hotter, the average kinetic energy of all of its constituent particles gets higher and higher. So that means the electrons are bouncing around at higher velocities. And all of the nuclei, the atoms without their valence electrons, are sort of vibrating at a higher frequency too. So they're moving all over. It's easier for electrons to bump into them. And so typically as the temperature increases, the resistivity will increase as well. So as we'll see, what we'll do is we'll define some reference temperature. And as long as we're close to this reference temperature, then the dependence of the resistivity on temperature will be linear. So the equation looks something like this. The resistivity is equal to this constant. Ooh, that's a plus. It's 1 plus the temperature minus the reference temperature. So this temperature is measured in degrees Celsius usually. Our alpha here is called the temperature coefficient of resistivity. And as we said, this was our reference temp. So as long as we don't get too far away from whatever this reference temperature is, this equation works well. So we can see that the resistivity increases as long as alpha is positive as the temperature increases. Okay. And so what is this rho naught constant that we have out the front? Well, we can see if T is the reference temperature, then this part is 0. And so the resistivity just becomes this constant here. So the resistivity at the reference temperature is our rho naught. And so this reference temperature could in principle be any number, but typically it's taken to be 20 degrees Celsius. So if you don't have a good feel for Celsius, this is about 68 degrees Fahrenheit, or exactly 68 degrees Fahrenheit. So 20 degrees Celsius is usually room temperature. Now, a degree Celsius is bigger than a degree Fahrenheit. So if we wanted exactly 70 degrees, this would be a fractional temperature. So 20 degrees is close enough. And because the resistance, because the resistance is linearly dependent on the resistivity, then the total resistance also has this exact same form. So the resistance is our resistance at the reference temperature times 1 plus alpha T minus the reference temperature. Okay. Now we are ignoring something here. We go back up to our formula here. As the temperature increases, resistivity is not the only thing that's going to increase, right? When things get hotter, they undergo thermal expansion. So they expand, so both the length and the area could change as well. But this will be relatively small compared to how much the resistivity changes. So we'll just ignore that fact and say that the resistance also has this exact form. So once again, as long as alpha is positive, if the resistance increases, or if the temperature increases, then the resistance increases as well. So let's just look at a few examples of alpha. There's a long list in your book that you can look at if you're interested. But for instance, copper has this coefficient alpha here of 3.9 times 10 to the minus 3. And then what are the units of alpha? Well, resistance is measured in ohms. This is also resistance, so it's also measured in ohms. So it has to be something that can cancel out the temperature here. So alpha is measured in inverse degrees Celsius. Okay, now this is pretty small. This is a decimal. This is pretty small. And so as you get hotter and hotter, the resistance of copper changes relatively little. And this is a pretty typical value of most metals. Now there are some substances, for instance, germanium and others, that actually have negative values of alpha here. So for germanium, this is. And so what that means, if alpha is negative, as the temperature increases, the resistance actually goes down. So far, we've only talked about two different types of materials. We've talked about conductors and insulators. Well, it turns out there's a completely different type of material, and these are called semiconductors. So these are conductors at certain temperatures, and they're insulators at other temperatures. And germanium is an example of one. So what's actually going on here is as the temperature increases, well, at a low temperature, there are no conduction electrons. So all of the electrons are bound to their atom, or maybe they're shared between a few atoms, but they can't move throughout the entire substance. But as the temperature increases, the average kinetic energy of all the particles increases. And so eventually you reach this threshold temperature where the electrons actually do become conduction electrons. And so they're free to move around the substance. And these are called semiconductors because they're conductors sometimes and insulators other times. All right, so let's do an actual example and calculate the resistance. So let's say we have some metal, it doesn't matter which one. And at 20 degrees Celsius, it has a resistance of 20 ohms. And it has a temperature coefficient of resistivity alpha of 4.9 times 10 to the minus 3 inverse degrees Celsius. And let's say that our temperature increases to 40 degrees Celsius. So first off, this is a huge jump. Just for reference, this is like in Fahrenheit, this is like going from 68 degrees Fahrenheit to 104 degrees Fahrenheit. So a huge jump in temperature here. And so let's see how much the resistance actually changes. Okay, well, we know our formula. Our resistance is our reference resistance at the reference temperature times 1 plus alpha times the change in the temperature. Okay, so our resistance, that's what we're looking for, is equal to our reference resistance, which is our 20 ohms here, times 1 plus alpha times the change in temperature. So our new temperature is 40 degrees Celsius, and our reference temperature was 20 degrees Celsius. Okay, so if you work this out, the new resistance is 20.1 ohms. So we literally doubled our Celsius temperature, or we went up almost 40 degrees Fahrenheit temperature, and our resistance only increased by about 0.5%. So extremely small. So we can see why Ohm didn't notice this, right? Whenever Ohm found his law, he said that the resistance was some constant that doesn't change as you increase the voltage. But in reality, the metal is going to heat up as you have a higher and higher current. But even if it does, we can see that its resistance changes by a very small amount. Okay, so this is something that we don't really have to worry about too much, at least if we have a small alpha. If you had a large alpha, then you could see some changes. Okay. All right, so the next thing we're going to talk about is electrical energy and power. So let me draw a circuit here. So say we have a very simple circuit. It has some battery, and some resistor. So remember, this is our symbol for resistor. It's just some squiggly lines. All right, and let's look at a few points here. So let's call this point B. Let's call this point A, this point C, and this point D. And let's also assume that A is grounded. So that means that A is held at 0 volts. And this is the symbol for grounded here. Okay, so A is at 0 volts. Then we go across the battery here, we can go around. And we know the direction of the conventional current. So remember, the conventional current is the direction that positive charge would want to go. And so they want to go from high voltage to low voltage. So they go around the circuit like this. Okay. Now, in reality, there are actually electrons that are doing this, as long as this is copper or some usual conductor. But we're always going to phrase things in terms of the conventional current, which is the flow of positive charges. Okay. Okay, so at some point, the current makes it to the battery. So it goes from point A to point B. If we have some amount of charge, delta Q, that passes through the battery in some amount of time, then the energy in the system has increased by that charge times the voltage across the battery. Okay, so this is the energy, the amount of energy that has been increased in our system here. And notice we don't get this energy for free. It comes from somewhere, like energy always does. And in this case, it comes from the chemical energy in the battery. The battery is a voltaic cell. There's some chemical reactions going on that you can ask about in chemistry class. And the net effect is that chemical energy gets used up and converted into kinetic energy in our electrons that are going around in our circuit here. Okay. Now, we know that wires do have some resistance, but we did an example last time and we calculated that the resistance of a 1 meter copper wire was significantly less than 1 ohm. So an actual resistor here is going to have a whole bunch of resistance, which essentially means that we can neglect all of the resistance that's in our wire everywhere else. Okay, so we'll assume as the charges pass through our wire, there is no energy loss. So in other words, we're assuming that they're not bumping into atomic nuclei or into each other or anything. They're just free to move through this wire. And they only encounter resistance when they go from C to D across the actual resistor. Okay. So as the charge travels from C to D, as the positive charges travel from C to D, they actually lose all of this energy that they were gained. So we talked about this before. If you go across a closed loop in a circuit, the total voltage has to add up to 0 as you go across. So we'll talk about this more in the next chapter. But essentially that means that all of the energy that we gain from going across the battery, we lose going across the resistor. And so where's that energy actually goes? Well, that kinetic energy, the electrons have kinetic energy, they bump into all of the nuclei, and they transfer that kinetic energy to them. So this energy gets transferred into heat. So the way the energy goes here is it goes from chemical energy in the battery to kinetic energy in the electrons, and then ultimately into heat in the resistors, okay? So as the charge goes around, it doesn't keep gaining more and more and more energy. It gains some amount of energy and then it expends it as it makes one full loop. And all of that goes into heat. Okay. So if we look at the power here, so remember power is the amount of energy or work done in some amount of time. And for the instantaneous power, we have to take the limit as delta T goes really small. So let's do that. For the power that's being dissipated as heat in our circuit, well, we know the energy is delta Q times delta V. This is how much energy is being converted into heat. And then we can divide by delta T and insist that that delta T be really small. That's all this thing here means. But this here is exactly what we defined to be the instantaneous current. So the power in a circuit, the amount of energy that gets converted to heat per second, is the current times the change in voltage. Now remember that power is measured in watts, which is the same, 1 watt is the same as 1 joule per second. So let's see if the units actually add up here. Well, current is measured in amps, which remember is a coulomb per second, and voltage is measured in volts, which is a joule per coulomb. So when we multiply these units together, the coulombs cancel out and we get joules per seconds, which is the same thing as watts, okay? So this really is the power that's in our circuit here. And we can come up with some other expressions for it as well if we use Ohm's law. So Ohm's law tells us that the current is equal to the voltage over the resistance. And so we can sub in either for I or for delta V here. And what we find is that the expression for the power is this, as we already saw. But we can also write this as I squared over R if we plug in delta V from Ohm's law into here. Or it can also be the voltage across the circuit squared divided by the resistance if we plug this in directly for the current here. Okay. So all of these are equivalent expressions that tell us how much energy is being converted to heat in the circuit per second. And it doesn't necessarily have to be heat. For instance, if you have a light bulb, then that power is getting converted into light energy. Or if you had a blender or something, it could get converted to the kinetic energy in the motor. But this is, in any case, this is the power in our circuit. Now, I guess you guys are probably too young to actually pay any electric bills. But the electric company doesn't charge you by the joule. It charges you by something called a kilowatt hour. Now, this is sort of a puzzling unit here, but it is a unit of energy. Right? Kilowatt is energy per time. It's a unit of energy per time. And then an hour is obviously a unit of time. So when you multiply these together, you do get a unit of energy, even if it's a weird one. And so let's see how much energy it is in joules. Well, 1 kilowatt hour, that's 10 to the 3 watts. And then we need to multiply by 1 hour. But since a watt is a joule per second, let's multiply by an hour in seconds. Well, 1 hour is 60 minutes. And 1 minute is 60 seconds. So if we multiply 10 to the 3 by 3,600, which is the result of this multiplication, then we'll find that 1 kilowatt hour is 3.6 times 10 to the 6 joules. Okay, so this is what they charge by. 1 joule of power or 1 joule of energy in your house would be very small, so they use this much larger unit. All right, so let's do an example. Let's say we have a light bulb that's hooked up to a battery. And the battery has a voltage of 12 volts. And the light bulb has a resistance of 30 ohms. Well, let's suppose this is the only thing in the circuit. We only have a battery and our light bulb here. So let's calculate the power. Okay. Well, I have a whole bunch of different expressions for the power. I wrote up here. And I can use any of them that I want. And I have the voltage and I have the resistance. Oops. So let's use the one that directly has those in it. That would be this one. So I don't have to calculate the current if I already have these things. So our power is our delta V squared over R. Now, because the voltage has to add up to be 0 across the circuit, the voltage across our light bulb must also be 12 volts. And then I just divide by the resistance. So if I do this, I get 4.8 watts. So that means there's 4.8 joules of energy every second that are being released by this light bulb. This will be as a combination of heat and light, by the way. Okay. Now we can also measure the current that's going through the light bulb by using Ohm's law. So we know that the current is the voltage divided by the resistance. So this is our 12 volts divided by our 30 ohms. So we have a current of 0.4 amps going through our light bulb. Now we could have also found this first if we wanted to, and then used our other version of the power formula. Doesn't really matter. Now let's see how much energy is released in 1 hour. Well, our power is the amount of energy per time. So as long as the power is constant and it doesn't change, which is a pretty good approximation in a light bulb as long as it's been on for a while, right? As soon as you turn on a light bulb, it's dimmer, so the power is lower initially, but then ultimately it powers up to its highest power, and it more or less stays there until the bulb starts going bad. So let's assume this is an hour over which the power was constant. So in that case, I can invert this equation, and we can find the amount of energy that was released in that hour is the power times the hour. So we calculated our power already. It was 4.8 watts. We multiply it by 1 hour. That's 3,600 seconds. And we see that's 17,280 joules of energy. Or if we wanted that in kilowatt hours, we could just convert this to kilowatts. So that's 0.0048 kilowatts. And then an hour in kilowatt hours is just an hour. So this is 0.0048 kilowatt hours of energy. Okay. Now a typical price to pay for a kilowatt hour is about 10 cents. So that's 10 cents per kilowatt hour. So if you wanted to know how much the company charged you to keep your light bulb running for an hour, well, we can just multiply these things together, and we'll see that the cost that you would have to pay is $0.00048. So less than a cent. Not too bad. All right. So there's one other thing that we're going to talk about, and that's superconductivity. So some substances have this property called superconductivity, where there's some critical temperature where if you're below this temperature, then the resistance is approximately 0. It's not actually 0, but it's really, really, really close. So if we look at one of these, like mercury, for instance, if we plotted the resistance versus the temperature, here, let's say here's the critical temperature. Well, we already know that the resistance is supposed to be linear with the temperature. So up here above the critical temperature, let me use a different color. Up here above the critical temperature, it's approximately linear. And then all of a sudden at the critical temperature, it falls to 0, and it's 0, that's supposed to be 0, everywhere below. Now, it's not really zero, but it's extremely, extremely, extremely small. And so for mercury, this critical temperature, black, is about, it's a little over 4 Kelvin. So remember, Kelvin is a system of measuring temperature where 0 Kelvin is absolute zero. So what that means is, we just talked about this, temperature is related to the average kinetic energy of the constituent particles of your substance. So at worst, they could not move at all. That is the lowest temperature. You can't have any temperature lower than every single one of the particles being absolutely still. So that's called 0 Kelvin. And then other than that, it works like Celsius. So 1 degree Celsius, a change in temperature of 1 degree Celsius is the same as a change of 1 Kelvin. So 4.1 Kelvin is very, very, very close to absolute zero. So it's extremely cold. So it's not surprising that something really crazy would happen at such a low temperature. And turns out for the vast majority of the substances that obey this behavior, their critical temperature is somewhere in the 1 to 10 Kelvin range. So you have to get extremely cold for this superconductivity to happen. Okay. Now, one interesting thing is that copper, silver, gold, a lot of the really good conductors that we use all the time are actually not superconductors. So it doesn't matter how cold you get, none of these things are going to ever have zero resistance. It's just going to keep decreasing and decreasing and decreasing. Now, if you actually got to absolute zero, maybe, but it turns out because of thermodynamics, you can never decrease something's temperature all the way to absolute zero. It would take an infinite amount of time. Okay. So these things are not superconductors. So there's a lot of weird objects that are. But one interesting property that they have is because the resistance is zero, or at least very, very close to zero, once you start a current going, so once you apply a voltage and that creates a current, here's another version of Ohm's law here, the current starts, but because the resistance is zero, you can then remove the voltage and the current will be maintained. So in fact, we have some superconductors in labs where there's no applied voltage, but a current has been going for years and years and years because at one point they applied a voltage. Okay, so we can see even if the voltage is zero, if our resistance is also zero, then our current can have a non-zero value and Ohm's law can still be satisfied. Okay, so one of the big names of the game now for superconductivity is finding high temperature superconductors. So high temperature could mean different things, but starting in around the 80s, in the 1980s, oops, someone found a way to have superconductivity around 40 Kelvin, which is still extreme. That's 40. That's still extremely, extremely cold, but much warmer than they were having it before, right? It was in the 1 to 10 Kelvin range, and now we're up to 40. So as of, at least at the time your book was written, the highest one that we found so far, the highest critical temperature is 134 Kelvin, and it's in this really weird compound that's been constructed of mercury, barium, cadmium, copper, and oxygen. So this is its chemical formula. And we were able to make it obey or to have superconductivity at this relatively high temperature of 134 Kelvin. Now this is still really cold. This is on the order of negative 200 degrees Fahrenheit. So very cold, but much, much warmer than before. So for reference, 10 Kelvin is about negative 400 degrees Fahrenheit. So ideally, the best case scenario is if we could find some object that has superconductivity at room temperature. So you're probably wondering, what is the point of superconductivity? Well, we use it a lot to make really strong magnets. So the normal way that we make magnets, as we'll see later in the course, is that we run current through a loop, which creates a magnetic field, which creates a magnet. Now, if your resistance is 0, though, you can get extremely, extremely high currents, which creates very, very, very strong magnets. And so what do we need these magnets for? Well, one place that we need them is in MRIs. So in MRIs, there's a giant magnet that, you sit inside of it, it turns itself on, it looks at your inside. And so we need really, really powerful magnets for that. And one way to get those is from superconductivity, okay? And so the way that we do this now, because we have these really, really cold substances, or these critical temperatures that are really low, is that we have to have liquid helium. And it turns out helium is not something that there's a huge abundance of on the planet, at least not in usable form. In fact, we've been running out of helium for decades now. So if we could somehow avoid having to use helium there, then that would be a really good thing. All right, so this is all the important stuff in the last part of this chapter. Hopefully I'll test negative tonight and we'll be back to normal class on Monday. All right, thanks.